We begin the Chapter 7 review, in which we go over alkenes and maybe some alkynes, I don't know yet. But for number 1, we're asked to find the name of the compound. Well, I noticed that we have a Z and E answer choices, right? Z stands for Zusammen, and E is for Entgegen, which is German, right? So these German chemists were saying that a Z, that just means that something is cis, so you could think of Zame, right? So it could be like the same side, right? The same side. Very, very silly, but it works. And E is going to be for trans. Okay, so that's trans. That's on opposite. Okay, so it's on opposite. So what I would do here is I would look at the double bond, not the triple bond, because you can't have cis or trans relationships in a triple bond, but you can have a cis and trans relationship with a double bond. So I will look at my double bond first. So how do I find if something is Z or E? Well, I go over here and I look at these two carbons right here and right there, right? And I want to notice that, you know, this carbon doesn't have 4 bonds explicitly. It has 1 bond kind of like implied. So I'm just going to have my hydrogen right there, okay? Cool. So let's see, this carbon has 1, 2, 3, 4 things attached to it, and this carbon has 1, 2, 3, 4 things attached to it. So now we start doing the cis and trans relationship, right? Well, let's see. This carbon, we're going to focus on this guy first, okay? So this is going to be carbon number 1. We're going to do it in this nice blue color. I look at what's attached to that carbon. So this carbon has a hydrogen attached to it. And then this carbon has a carbon which is triply bonded, okay? So ask yourself, well, which is better? Is a carbon better than a hydrogen? And you say, yeah, Brian, a carbon is better than a hydrogen. And so this one is going to take precedence, is going to be number 1, and this hydrogen is going to be number 2. Okay, so now we go on to the other carbon, and we're going to do it in a darker blue, almost purple. We're going to look at this carbon right here, and focus on these 2 guys, okay? We don't focus on that guy. We focus on the group that's attached to the carbon. It's weird, but well, I'll do more practice problems doing E and Z naming structures, right? But for now, it's just kind of like divide the structure in half and just focus on the right side and focus on the left side. So now you're saying, well, we have a CH3 and we have an alcohol. Which one is better? Well, you know, America runs on alcohol, right? And so we obviously care about alcohol more than we care about methyls, right? And so we're going to say that this is number 1 and that this right here is number 2, right? And so it just kind of goes over the chapter 5 concept in which you're giving priority. And so oxygen is more heavier than carbon, right? So oxygen is more important. In this case, a carbon is heavier than a hydrogen. And so we take that as a priority, okay? So it's just the same prioritization method. Okay, so now you're noticing that, well, your 1s are on opposite sides, right? So we have a 1, we have a 2, and a 2. You know, that's trans because 1 moved and 2 also moved. And so that's trans. This would be cis, right? Because 2 is on the same side, 1 is on the same side. But for our compound, it's going to be trans. So what's trans? Is it Z? We'll say no. It's not Z because that's cis. This is a 1, 1, 2, 2. Trans would be a 1, 2, 2, 1. That would be trans. This is E right here. This is what we have, right? We have a, well, it's not what we have, but we have a trans relationship. Okay, that's what I'm trying to say. So automatically we can get rid of A because that's Z, D and E because those are Z's. Okay, those are Zusammen, which is cis. If you want to be fancy, you could say Entgegen for E, right, with a German accent. If you don't say it without a German accent, it's incorrect. That's what I believe. So it has to be either B or C. Okay, so now that we got that sorted out, we're going to start naming this. So what we have here is that whenever you're naming compounds, remember nomenclature, you're going to start at the alcohol first. You don't care about the triple bonds or double bonds, you care about the alcohol first. You want the alcohol to be on the lowest carbon number, right? And then you want your longest chain to include the double bond and triple bond, right? So this is going to be carbon number 1, this is 2, that is 3, 4, 5, and 6. Okay, so for sure I'm going to have hex. Let's see, hex is in the same part, okay? And we have an alcohol on the first carbon, we have a double bond on the second carbon, right? So that's a 2-ene, and we also have a 2-methyl. And we have a triple bond on the fourth carbon, so that's going to be 4-ine, right? So let's see, what do we have here? B is incorrect because they're saying that you have an alcohol on the sixth carbon, and that's incorrect. They're counting from here. That's wrong. So again, B is incorrect because they were counting from left to right. You should be counting from right to left. Count from the alcohol first. So C is going to be correct because you have your alcohol on the first carbon. So C would be your answer. Okay? All right. So now we move on to question 2. Which alkene will liberate the most heat per mole when we do catalytic hydrogenation? Well, whenever it says most heat, that means most unstable. Okay? That's most unstable. Now, the least amount of heat, that is equal to more stable. Okay? And what you should know is that kind of like interior double bonds will be stable, and that terminal is going to be unstable. And so terminals give out more heat and internals give out less heat, right? So when I'm talking about internal, I'm talking about a double bond that is within the molecule. So this is internal, that is internal, this is internal, and that is internal as well. However, A, right, would be terminal because it's at the end of the molecule. It terminates the molecule. That's what it means. The last guy, if we had a double bond right here, that would be terminal. If we had a double bond there, that would be terminal, 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 also terminal. Okay? So it has to be on the last carbon. And those give off the most heat. They're going to be the most unstable. Usually you'll see that with Hofmann, right? And not Zaitsev, right? Because Hofmann, you get one substitute, and then with Zaitsev you could get like 2 in this case. So that's 2, you see? And so Zaitsev would give you internal double bonds usually, and typically Hofmann gives you external, or I should say terminal double bonds. And so A would be the answer choice because it would be unstable, right? And typically you would see that with Hofmann reactions, they are not stable, right? Zaitsev would be internal, Hofmann would give you terminals. So now we will be doing a reaction with ethyl oxide and sodium ethoxide, or so whatever this is, ethanol, sorry. I don't know what I was saying. Ethanol and sodium ethoxide, right? So what happens here in this reaction, and notice that this is an E2 reaction. I know this because we have sodium, which is a metal. And so metals, they are strong. And I don't like that, so I'm just going to erase this. They tend to be strong. And of course we have heat, and that equals an E2 reaction. Okay, that's an E2 reaction. So what happens during an E2 reaction, if you remember? Well, what happens here is that this double bond breaks off, and we form a carbocation, right? And carbocation, And notice that we have to form a double bond because this is an elimination. We're not expecting any substitutions. We're not expecting anything coming in. We're just going to do some, some beta hydrogen shifting. So I'm going to draw out my hydrogens right here. We have some hydrogens right there. Okay. Do we have any hydrogens over here? No, we don't, because that carbon has 1, 2, 3, 4 bonds. 4 bonds, and so it doesn't have any hydrogens to give up, right? Now, here comes the question. Do I want to form it over here? Do I want to form my double bond over there, or do I want to form my double bond over there? Well, you should be saying you want to form your double bond over here, right? Why? Well, if I formed it to the right side, then the problem is that carbon has 5 bonds. We have 1, 2, 3, 4, 5. And that's not possible, okay? That's not possible. So the only logical thing that I can do in this problem is form my double bond to the left, right? And so I should be expecting an answer choice that has my carbon, or that has my chlorine taken out, okay? So this looks good. Over here, this would be incorrect, right? Because your chlorine bond didn't come off. Also, what happened to your methyl groups? Over here, your methyl groups they're not supposed to change, right? But it changed, and so B, C, D, and E are incorrect. Your methyl group stayed the same, and you put a double bond towards your left side. And that makes a lot of sense to me. So I'm going to say that A is your answer choice, and we are good. Now we're doing a reaction with sodium iodide and acetone. Well, acetone is aprotic. That means it doesn't have any hydrogens to release. And sodium iodide is very strong because it has a metal and also has a great halide, right? And so for an aprotic reaction, iodine is kind of favorable to do, right? So sodium iodide, that looks pretty good. And I would say that that would be an SN2 reaction. Let's see, we have a halide with a secondary carbon that looks like a 20. So I want a secondary carbon right there. Okay. So first of all, what it's saying here is that in step 1, we're going to be treating this molecule with sodium iodide in acetone solvent. And afterwards, we're going to be treating it with T-butyl hydride, or whatever that's called, and T-butyl potassium oxide. I don't know what that's called, but right? So what do we do? Well, in step 1, what happens is that we're going to do an SN2 reaction, right? It's an SN2 reaction. And so the sodium iodide comes in, and first of all, this chlorine pops off, right? It comes off, and let me draw off my hydrogen. So first of all, this portion of the molecule is chiral. It's chiral because there's a CH3 right here, a CH right there, a hydrogen, and the chlorine. So those are 4 different groups, and it's chiral. So what do you know about chiral SN2 reactions? Well, you have to do an inversion. If chlorine was hashes, it's going to be a wedge. Oh, well, not chlorine, but whatever comes in is going to be a wedge. So for this case, I know that iodine should be a wedge, right? It should be a wedge when I'm done with it. Okay, so now we formed this guy, right? This chlorine came off, and this wedge became flat. It just became a line, right? And now we have a carbocation, right? So that is a secondary carbocation. Okay, this iodine sees the positive sign, and he's very attracted to it. So he goes and links up, and this chlorine is attracted to this sodium, and they go pair together, right? So now we have this guy. Notice that the iodine is now going to be a wedge, and my hydrogen is going to be a hash. Okay, so that was step 1. Now we have to treat this guy with these materials, right? Now here's something very important, something that's super important. It's important for you to know that we will not be favoring Zaitsev's rule. We will actually be favoring Hoffman. How do I know that? Well, we're working with big, bulky bases. And I'm just going to give you the rule right now. Whenever you have anything with T-butyl, like T-butyl OK or T-butyl OH, that's going to be Hoffman favored. So we're going to write a heart and maybe an arrow right there. So Hoffman, right? And whenever you're working with, let's do it in a different color. Whenever you're working with ethyl oxide, let's do ETO negative, right? That's going to be Zaitsev favored, or it could be ETOH, or anything with OH right there. So these are going to be Zaitsevs. If I spell that right, let's just say I spelled it right, okay? So these are going to be Zaitsev favored, okay? And that's a bad heart. The reason why they're Zaitsev favored is because they're small. And they're very strong, and they could get into nooks and crannies very easily. However, Hoffman are very big and bulky. Bulky and big, right? And so your T-butyls are going to give you Hoffman reactions. Your small bases and nucleophiles are going to give you Zaitsev, like sodium hydroxide or potassium hydroxide, OH, ETH, ETO, I mean, right? Those are going to give you Zaitsev. Since we're working with T-butyl, we're going to expect Hoffman. Okay, so what happens here is that we're going to do an elimination reaction. And so this iodine breaks off, and we form this right here. Right? And now we're going to be working with our beta hydrogens, right? Because this is kind of like an elimination reaction. Right here. Let's do it right there. Okay, so which one am I going to prefer? Is this hydrogen going to break off, or is this hydrogen going to break off? It doesn't matter. For the right side, it could be this guy or that guy. Doesn't matter, right? Which one am I going to favor? Am I going to favor Zaitsev, or am I going to favor Hoffman? Well, I'm going to favor Hoffman because we're doing a what? We're doing a T-butyl elimination. Okay, so let's say that the hashes come off, and so they come over there, and we get this, right? So that's what we get. I'm ignoring this hydrogen. It's just implied, right? It's just implied. So that's the Hoffman reaction. That's going to be correct. Over here, this would be the Zaitsev, which is not correct, right? That's Zaitsev. It's very easy to show that you have two bonds attached to that double bond. Over here, you only have one bond attached to that double bond. And so this is going to be more unstable. Notice that it's a terminal double bond, and they're going to release more heat. This right here would be a interior or internal double bond. They release less heat. That would be more stable. But that only occurs with very small nucleophiles, very small bases. We're not working with that. We're working with T-butyl. And so we're expecting a terminal double bond. Why? Well, a T-butyl, right? T-butyl hydroxide, when it comes in, let's see if I can remember it correctly. Let's see. I think it's like this. Don't quote me on this. I don't know. So T-butyl, you need like 4 of them. 3, 4. Let's do that. So 1, 2, 3. Let's see, T-butyl 1, 2, 3, 4, and then hydroxide. 1, 2, 3, 4. Yeah, so something like that. T-butyl hydroxide. If it tries to go towards the methyl group, it's going to be repelled by hydrogens, by carbons of like charges. And so it's not going to go as as close to the stable part, right? So since it's big and bulky, it's going to be repelled by this carbon. And so we're not going to be able to go closer to the stable region of the molecule. Therefore, it's going to go kind of further away from the carbon, right? So it can't go there because it would be repelled. So instead it goes to the next big thing, and it goes over here to the terminal, right? So that's why we prefer Hofmann for big bulky bases, okay? All right, so you're probably wondering, well, that's not an answer choice. Well, it is. It is an answer choice. What if we grabbed the molecule and we turned it over? Well, we would get this. If I can clearly draw this wedge would be a hash because it's turned over, and your double bond, I believe, would be to the left side. And so it'd be D. That would be the correct answer choice, right? And so that's just really testing you on Zaitsev's and versus Hofmann when that would occur. And it tells you about the stepwise procedures whenever you're doing reactions, right? So first you're going to do an SN2 reaction, and then afterwards you're going to do an elimination reaction that favors Hofmann, right? Okay, so which compound listed would you expect to be the major product when 2-bromo-2-methylbutane is refluxed with potassium hydroxide and ethanol? So refluxed just means that you have something with heat. Okay, so that just means heat. Let's say that you have a flask with your material in it. Let's say that this is a heating pad, right? So we have a fire, and that's what it means. It just means that we're doing this process over heat, right? So that's very important, I believe, for this question. As always, write out your molecule. So we're working with 2-bromo-2-methylbutane. There's no cyclo, so it's not a shape. So we have butane, that's 4. So 1, 2, 3, and 4. Okay, so there should be a bromine on the second carbon, and there should be a methyl group on the second carbon. Now it's completely random how I drew this. The methyl group could be on the wedge, the bromine could be on the hash. It doesn't matter. It's preference, really, right? And we're reacting this with potassium hydroxide and an ethanol solvent. So let's call that ETOH, ethanol, right? Okay, so ethanol is going to be protic, right? And it's also kind of weak. And this is going to be strong, right? So it's strong, and yeah, it's small. Also, this is small as well. So we have small solvents. Okay, so since it's strong, it's not going to be SN1, it's not going to be SN2, right? And this is a secondary carbon. Are we working with T-butyl? No, we're working with ETOH, right? Ethanol. And so we're small, we're going to be favoring Zaitsev's rule, right? Okay, so what happens? What happens in this reaction is that this bromine comes off, right? So we have a methyl group right there and a positive carbocation. We're going to draw in our how should I say, hydrogens. And we also have one right here. Automatically, you should know the answer already. Since we're doing elimination, we're not doing any substitution. A and B are clearly substitutions, so they're incorrect. Now, we are working with a small base, small nucleophile, right? And so we should be favoring Zaitsev's, right? So Zaitsev is going to give us an internal double bond, not a terminal double bond. And so C is going to be incorrect because that's a terminal. It happens in the end, right? So that's going to be wrong. E is also wrong because that's terminal as well. That's wrong. D is going to be your correct answer. Now, if you want to see it worked out, I could do that for you, right? So if you want to see it worked out, here we go. You could skip ahead. Doesn't matter. Right there, a hydrogen would actually pop off and go over here in this direction, giving us this guy. Here's our methyl group. It was in the wedge, or it was hash, but when that bromine came out, it became flat, and so it became a line, right? And Now you see that Zaitsev is favored because it's a small base. It's an ethanol. So you have 1, 2, 3, right? So that's 3. That's going to be favored. Of course, you don't see that as an answer choice, but what if we got this carbon right here and flipped the molecule this way? So we would have this guy, trying to draw it out right here, and you'd be there. And then what if we got the same molecule from this carbon and we flipped it that way? Well, you would get this. Right? So something like that. And that's answer choice D, right? So that would be answer choice D. Okay. What happened if instead we ignored this double bond and we put it over here? What would you get? You would get 1, 2. So that would be disubstituted. It's not stable, right? Because it's terminal. That's going to be Hofmann. And that's not good, right? You would expect that with T-butyl, right? But for this one, you're going to expect some Zaitsevs, right? For ETO. Also, I just wanted to pull you aside and say that whenever you see ETO, when they have ETO, H, or just ethyl, whatever, right? Or it could be like ETO negative with sodium hydroxide, or not sodium hydroxide, just sodium. Well, whenever you see ETO, think of an E2. So this E right here, that goes for E2 reaction. Right. So if you're doing anything with ethyl hydroxide, ethyl oxide, or whatever, think of an E2 reaction. Okay. And also T-butyl, they're gonna go for E2 as well. So E2, okay, and then E2 or T-butyl, I believe it was T-butyl hydroxide. Yeah, those are gonna do E2 reactions as well. Right. Except you're gonna expect some Hoffman. And over here, you're going to expect some Zaitsev. Let's draw this out. So that's Zaitsev, and this is going to be Hoffman. Okay. Okay, so what happens when we have, I don't know what that is, obviously. What happens if we have this guy with a solvent, right? So I believe that's like, oh man, I think propane, right? So propanol, right? And then I'm not even going to try to name that. But what would we do? Well, first of all, we have potassium, so it's strong. And we're doing with the protic solvent because we have a hydrogen that could pop off and kind of mess with us. And so because we're doing with a protic solvent, most likely you're not going to be doing SN2 reaction. It's not going to happen. SN2 reactions, they favor aprotic solvents, right? Because the hydrogen could repel you and you don't want any steric hindrance. Also, a dead giveaway, we're doing heat. So the main question was, are we going to do an E1 or E2 reaction? The potassium shows me that we're strong, right? And so we're going to do an E2 reaction because that's strong, okay? Now, I have to determine what are we going to do. Are we going to do Zaitsev or are we going to do Hoffman? Well, you know, I'd rather prefer a Hoffman. Why do I want to prefer Hoffman? Well, I want to do this because it's big and bulky. And so, you know, that's going to be Hoffman favored. You know, Hoffman favored. And, right, so, let's see. It's Tata. Anyways, since we're doing a reaction, right, what happens here is that this bromine is going to come off, and this is elimination. So what we have now are 2 methyl groups and a plus sign, okay? Right, so let's draw our beta hydrogens. Did this carbon have any beta hydrogens? No, it doesn't. It already has 4 bonds. So the only thing that we can do right here is have our hydrogen right there. and maybe some hydrogen right here. I don't think that's going to react anyways, right? So what should we expect? Well, since we're doing a Hofmann reaction, you should expect that this, either the wedge or the hash hydrogen should come over here and make a double bond. And so you should be having this guy with a double bond right there, okay? Also notice that you cannot put a double bond over here because carbon would have 5 bonds. That's 1, 2, 3, 4, 5. That's illegal, right? You would get sent to prison. So that's not good. Right here, you're not violating any octet rules. It's pretty good. It's Hofmann favored. It's a terminal double bond, so it's not going to be stable. It's going to release the most heat. So the answer choice is kind of in formulas, so that might freak you out. But what it's saying is that this carbon, let's say that this guy right there, is going to have a CH3. That's a very bad CH3. A CH3, a CH3, and a CH2. Sorry, CH, and this is a CH2. Okay? So when we have a parentheses in CH3, this just means that we have 3 methyls, and they're attached to this carbon. That's a carbon right here. They're attached to that carbon, and this carbon is singularly bonded to a CH, and that CH is double bonded to a CH2. That's what it means. So you see anything like that? Well, yeah, it's actually going to be answer choice B. Now we have to figure out which alcohol would initially produce the most stable carbocation when treated with concentrated sulfuric acid. Sulfuric acid. So for the most stable carbocation, that's going to be a tertiary carbocation, right? So basically, it's saying that whenever, I'll do the reaction for you too. I just want to get this out the way. Whenever this hydroxide pops off, you're going to form a carbocation. And this is going to be the most stable because 1, 2, 3 carbons. That's a tertiary. So it's going to be really good, super stable, okay? Whenever this comes off, you form a carbocation. It's 1, 2, that's a secondary. That's a primary. This is another primary. And this is going to be a primary as well, right? So that's not good. For stability, a tertiary is going to be better than a secondary, and it's going to be better than a primary, right? Okay, so now let's actually do the reaction. So what happens in this reaction we're doing with a concentrated sulfuric acid? Oh, by the way, since this is a tertiary carbon, you're not going to have a lot of sulfuric acid to work with, right? You don't need as much because already this is a very easily manipulable molecule, right? And so what I'm trying to say is if you're working with a primary carbon, you're going to need like a gallon of sulfuric acid and a lot of heat. But if you're working with a tertiary carbon, you need like a millidrop of sulfuric acid, maybe like 10 degrees. I don't know. It's just really stable, not as dangerous, not as aggressive, right? So the more, how should I say? If you're a tertiary carbon, you're just going to be reacting very smoothly. If you're primary, it's going to be very aggressive, very dangerous, not as favorable. So what happens here is that, first of all, this hydrogen goes away from this oxygen, and this alcohol is partially negative, right? It's partially negative because it's attached to this carbon. So over here, you have a positive carbon, and over here you have a negative oxygen. And so this hydrogen is positive, and so this oxygen bonds with that hydrogen. What do we get? We actually get an alcohol that became a water. Okay, and you have some negative oxygen right there. Okay, afterwards, this water is going to pop off. Why did we have to do this? Well, notice that hydroxide is a pretty bad leaving group. Not good, right? But water is a great leaving group. And so we want to form water when we do a reaction. So again, this water molecule comes out. Right here, we form a carbocation right there. And right here, this water is going to be just hanging out, right? And so notice that we made a negative oxygen. Well, you could leave it like this, but I want to do it to completion. Most likely, this hydrogen is going to come off of oxygen and is going to be attracted to this oxygen right there. So we reform the sulfuric acid and we make a hydroxide group, right? So there we go. Now we're going to worry about this guy. What happens to him? Okay, well, over here we have some alcohols, or some hydrogens, right? Which am I going to prefer? Am I going to prefer to take a hydrogen right here? Am I going to prefer to take it from here or there? Well, we were working with one hydrogen and we just kicked out a water, right? They're very small molecules just reacting, not really big. This guy doesn't actually come into contact with us, so he's not trying to get near us. We're just borrowing stuff from him. And so nothing big and bulky is really coming into contact. So what should I expect? Well, I should expect what? Zaitsev. Okay. So am I going to form it here? No, that's Hoffman, right? That's terminal. This is also Hoffman. This is Hoffman. But this right here is Zaitsev. And it would give us a 1, 2, 3. It would give us a tertiary or a tri-substituted molecule, right? Internal. And so that would actually be the preferred one. And so you should get a molecule that looks like this. Okay? And that would be the end product for this reaction. What would be the major product of the following reaction? I'm not going to actually do the reaction. By the way, this is a deuterium, which is just very heavy hydrogen. It reacts the same way, it's just fatter, it's a bit thicker, right? And so what you're really looking for, this question is asking you, do you know anti and do you know syn reactions? So whenever you do these reactions for alkenes, you should know that E2 cis is bad. Okay, cis is bad, but trans is good, right? So trans hydrogens can form double bonds. Trans deuteriums or whatever can form double bonds. However, cis hydrogens cannot, right? Because that's a lot of steric hindrance. So what we're really asking for is we need a cis hydrogen or we need a cis deuterium, right? So here's what you do. Over here, you see that this methyl group right here, well, we don't care about this deuterium because automatically it's going to be not reacting with us, right? It's a part of the same carbon. So we're going to be reacting with stuff that is on a different carbon. Okay. Well, this deuterium, which came from this guy, so we care about deuterium in this reaction, he's going to be cis because we're going down. This methyl group is going down. That deuterium is going down as well. Hence, that's not favored. So it's not 2. For this methyl group, that's going upwards. This is also going upwards. That's going to be cis. That's bad. These are on different carbons, right? So most likely it's not good. It's wrong. So I should actually be reacting with this guy over here. Okay. So 5 is wrong. Over here we have a methyl group that's going upwards, and then we have a deuterium that's also going upwards, so that's going to be cis as well. That's bad. But over here we have a methyl group that's going downwards, and then we have a deuterium which is going upwards, so that's going to be trans. That's going to be anti, right? So this is called syn. It means same face, means cis, right? And this is going to be anti. Syn, anti. Syn complainer, anti complainer, right? So number 1 would be the correct answer. That's going to be the major product, right? You always want something that's trans. Okay. Now, what is a major product of the following reaction sequence? Well, over here you're acting with sodium amine, I believe. So what happens? What do we do? Well, you're going to have a doozy with this problem. And, you know, I probably need more room. Well, you know, amine, if I remember correctly, has like a pKa of, I believe, 38. And so this is an acid-base reaction, right? Also, you're making the, I believe this is called acetylide, right? Acetylide. So this double bond breaks off and forms a carbocation. Or not a carbocation, but it just forms a carboanion. And this amine picks up this hydrogen. So we have H, C, triple bond with a C, negative, let's make him happy. And we now have some ammonia, or ammonium, or whatever. I don't know. Actually, this should be negative, and this is going to be neutral. So that's ammonia. I don't know what that is. And, well, you know, might as well just say it first. Whenever you're making this guy right here, you should be favoring an SN2 reaction whenever you're dealing with a primary, right? And so you're going to favor E2 with a secondary or a tertiary, right? So secondary or tertiary. So this guy right here, he's locked and loaded. He's ready to go. He's like, well, you know, whatever you give me, it depends. I could do an SN2 reaction or I can do an E2 reaction, right? So, yeah, whenever you're doing this, you're just creating an acetylide, and now we have to react it with something. In this case, we're reacting with a CH3, CH2, CH2, bromine, and notice that this is going to be a primary. It's primary. So what do we know? He looks at it and he says, well, I'm not going to do E2 because you're not secondary and you're not tertiary. So most likely I'm going to do a primary because you're primary. Or I'm going to do SN2 because you're primary. So what happens here is that this bromine pops off, right? And now we form a carbocation, and he's attracted to this carbocation, and we form this. Actually, let's do CH2, CH2, CH3, okay? Afterwards, we're treating this with an excess of hydride, and I know it's a bit complicated because if you try to do the arrow pushing for this reaction right here, it's going to be really extensive. I'm not going to do it. I don't want to confuse anybody. So all you need to know is that whenever it says excess, it means that we have enough hydride atoms or molecules to remove all our triple bonds, right? So for instance, I would take one H2 to get rid of a double bond, or to get rid of this bond. I would take another H2 and get rid of that bond. And so what this guy is saying is that we have enough hydride molecules to get rid of all our triple bonds, right? So we should be having something that gives us 5 carbons, okay? Because we have 1, 2, 3, 4, and 5. And it should be straightened out. It should be kind of crooked. So 1, 2, 3, 4, 5. That's your answer. So these hydrogens just kind of like got our molecule and took away the triple bond, took away the double bond, and made us straighten out, made us even, right? And so I should not be expecting any double bonds. So A is wrong, C is wrong. I don't know where that nitrogen came from, okay? D is wrong. And so the only answer choice that makes sense would be B. Now we begin the kind of like my own version of lecture, I guess, because I felt like the chapter review for this chapter was a little short. It was just like 9 questions, and I don't feel like that's very suitable for you, right? So I want you to do well on your next exam, and I'm just going to be teaching you the ropes, right? So in this case, we're going to be doing just E and Z naming, right? We're not going to name it. We're just going to say, is this E or is this Z, right? And so E, that just means that's going to be trans, right? So we're experiencing a trans relationship. And Z is going to be a cis relationship, okay? Z is Zizamzide, right? Very obnoxious, very annoying, but I think it works, right? So, right, what happens here? Well, notice that you're going to be focusing on your double bonds, right? So on your double bond, you have a CH3, a CH2, CH2, a CH2, and a CH3, right? Okay, and this one is just a hydrogen, right? Okay, so I think everything's a bit obnoxious whenever you have too many things going on. So what am I going to prefer? If I split this in the middle, I'm just going to be focusing on the right side first, okay? This is what I do. What is better, a carbon or a hydrogen? Well, carbon is heavier. Carbon's like number 6 and hydrogen is number 1, so I'd rather have a number 6 than a number 1. So this is going to be priority number 1, this is going to be priority number 2. Now if I move on to the left side, I'm going to be focusing on only this guy right here, right? So what do I prefer? We have a CH2, we have a CH2, okay? We have a CH3, and then we have a CH2. Well, what's better? Do I want a CH3 or do I want a CH2? Well, I want a CH2, okay? Because first of all, you'd rather have a carbon, then a carbon with a hydrogen, then a carbon with 2 hydrogens, and then carbon with 3 hydrogens, right? And so if I could, I would just have carbon by itself. But in this case, I have a CH2 versus a CH3, right? And so CH2 is going to be better, right? So we have a CH3 right here and a CH2. So that's going to be better. This is going to be priority number 1. This is going to be priority number 2. Okay, so now I notice that I have 1, 1, 2, 2. 1 traveled over there, 2 traveled over here. So that's what? That's going to be E. That's trans, right? And so your answer choice for this one is going to be E, right? Okay. Now, the more you do, the faster you become. Over here, you think that there's only three things attached to that carbon. Turns out that there's a hydrogen right there. Okay. Well, let's see. Bromine is better than a CH3, so that's going to be priority number 1. This is going to be priority number 2. Then we have a CH2 versus a hydrogen. Well, I'd rather have a carbon and then a hydrogen right there. So 1 and 1 on different sides, that's going to be what? It's also going to be E for trans. Same shebang, right? So that's going to be 1, 2. That's 1 and 2. Notice that the ones are on the same side. Right? Alright, so since they're on the same side, it's going to be cis. And that is on the same side, so it's going to be Z over here. Z. Yep. Okay. So that's going to be 1, 1, 2, 2. That's going to be E. Obviously, this is cis, but just to double check, right? It's going to be 1, 2, 1, 2. The 1s are on the same side, 2s on the same side. That's going to be cis, which is a Z conformation. Over here, we have a hydrogen. This is going to be number 1, 2, 1, 2. That's going to be trans, so it's not Z, but E, sorry. And over here, hydrogen, so it's going to be 1, 2, 1, 2. 1s are on the same side. That's cis, Z. Z. Should be. Yeah, it's Z for cis. And gee whiz, wow, okay. This one looks like a baddie, right? But it's not. Notice that this is just a CH3 versus a amine, or whatever that is. And then you have a carbon that has an oxygen versus a carbon with hydrogens. What is it going to be? Well, you know, I'd rather have a nitrogen because it's heavier than carbon. So that's going to be number 1. This is going to be number 2. Now, do I want a carbon with an oxygen or do I want a carbon with a hydrogen? I want the carbon with the oxygen. So it's going to be number 1. This is going to be number 2. So 1s are on opposite sides. That's going to be E. Over here, we have a hydrogen, right? So that's going to be 1. This is going to be 2. Or, nope, sorry. 1 and 2. So 1s are on opposite sides, right? And that's going to be E for trans. Over here, we have a hydrogen. And let's see. CH2 is better than a CH3. That's going to be 1, 2. And anything is better than a hydrogen. So that's going to be 1 and 2. ones are on the same side, that's going to be what? Cis. Z. Right, so for this question, I want you to find which one is going to be the most stable, which one is going to release the most heat, which one is going to release the least amount of heat, right? So from 1 to 4, right? So 1 being the best, 4 being the worst. Well, the first thing that I would do is that whatever is the most substituted is going to be the most stable, right? So what I mean by substituted is how many bonds are connected to this double bond, right? In this case, we have 1, 2, 3 bonds attached, right? So that's going to be, let's call that 3, right? And over here we have 1 and 2, that's a secondary. Let's call this 1, 2, that's a di or secondary, I don't care. And that's 1 bond, so that's going to be the worst. So automatically we know that 3 is going to be better and 4 is going to be the worst because it's a primary, right? And now we have the issue of these secondary ones, right? The di substituted. Which one is better? Well, you know, it's actually this one. Why? Okay, well, let's do this. Let's do versus this guy. Okay, well, the reason why this one is more stable is because you're not experiencing any steric hindrance. What I mean is that these methyl groups, CH3 and CH3 right here, they're not close together, so they're not repelling each other, right? If you were close to each other, they would be pushing away, and that generates excess energy, and that raises the amount of heat that is released whenever you're doing a reaction. Over here, you have a CH3 and another CH3, and they actually collide, right? So they're so close to each other that they hit each other, and whenever they hit each other, they repel. And since they're repelling, they're trying to get away, they're going to generate heat, and that's not good, right? So the reason why trans is better is because you don't have that steric strain. So trans is going to be better, right? Notice that they're both internal. They're not terminal double bonds, but the trans one is going to be better. The cis one is going to be worse, right? So this is going to be the most heat. This is going to be number 1 for heat. This is going to be number 2 for heat, 3, and 4. So the most stable gives us the least amount of heat, and the least stable is going to give us the most heat whenever it does reactions. Now I wanted to go over Hofmann versus Zaitsev. When do we do Hofmann and when do we do Zaitsev? Well, Zaitsev, you're going to prefer it when you're working with small bases or nucleophiles. Okay? And Hofmann, you're going to prefer it, and I always write it with double F. It's actually M-A-N-N, right? So that's Hofmann, and man, I can't write today. Or any day. So Hofmann is going to be big, bulky bases. Or in this case, we have a lot of any 3, right? And that just means that we're working with triethylamine, and it's just N with this guy right here, right? So as you can see, it's pretty bulky, right? Because we have 3 ethyl groups attached to this nitrogen, and then like a lone pair. So that's automatically Hofmann, right? If you ever see that on the exam or ACS or in Nature or something, like if you're going shopping at Nordstrom and they have like triethylamine, right? Then yeah, you know it's going to be Hofmann. Okay, so what do we do? Right. So we're reacting with sodium hydroxide, and notice that this is going to be a what? What is this? This is a tertiary carbon. Okay, so it's a tertiary carbon. It's going to be strong. And is E2 possible? You know, I would say that E2 is possible because SN2 is not possible. Why? It's a tertiary carbon. And remember that for SN2 reactions, tertiary carbons always fail. They would typically work with primary carbons and secondary carbons. But E2 is going to take the cake whenever it's a tertiary carbon. Okay? Now, is this Zaitsev or Hofmann favored? Well, it's going to be Zaitsev favored because we're working with a small base. Sodium hydroxide is just an oxygen with a hydrogen, and that's pretty small. So it's going to be able to kind of maneuver its way into the molecule and become really stable and product favored. Okay, so we're going to be doing a Zaitsev reaction over here. Of course, this bromine pops off, forms a carbocation. And you know I love you guys, so I'm going to do all the steps for the reaction, right? So we formed a carbocation, a tertiary carbocation. That's really good, okay? After that, we have the beta hydrogens right here, And what am I going to prefer? Am I going to prefer these guys, or am I going to prefer these guys? It doesn't matter. All that matters is that I make the most stable product. So am I going to make a double bond over here, or am I going to do it over here? Well, you know, I'd rather do it over here. Why is that? Well, Zaitsev says that if I make a double bond right here, it's going to be the most substituted. Also is going to be an internal double bond. Now, if I did it over here, ignore this purple one, this would be a terminal alkene, or yeah, alkene, right? And it would be a 1, 2. That would be di-substituted. Not good. However, if you stick with the purple one, then we end up getting a 1, 2, 3. That's a tri-substituted. It's more stable. It's going to release the least amount of heat, and it's an internal alkene. So that is going to be Zaitsev favored. Let's call that Zait, right? Zait favored. Let's draw Tata right there. You know who you are, right? He's like a neutral face. It's a very bad drawing. Anyways, so now what if we did it with triethylamine, right? And if you didn't know what triethylamine was, then the heat would just be a dead giveaway that you're doing an elimination reaction. But notice that triethylamine, in this case, is going to be very big and bulky, so it's going to be for Hofmann, right? And so it's still an E2 reaction, but it's just going to have a different placement. Since it is a Hofmann favored reaction, it's going to be like this, and we're actually going to favor the terminal alkene. Okay, so this is Hofmann. And you know, someday I hope that people remember me like Hoffman, right? Probably won't happen, but you know, I could dream. I just want to be remembered, right? Okay, now we are dealing with this guy right here, and notice that this is going to be a secondary carbon, and that's a positive, that's a negative, so it's going to be strong, right? So it could do SN2, or it could do E2 reaction. Gee whiz, okay, that's not good. What do we do? Well, you know, I'll say for time's sake, let's just do an SN2 reaction. Let's do an SN2 reaction, okay? Because let's say that we're not giving any heat, which we're not. So let's assume that we're going to do an SN2 reaction. So SN2 reactions is bromine pops off, forms a carbocation. It's a secondary carbocation, so it's not that favored. And now this oxygen, this methoxide, is attracted to this positive carbocation. So it goes over here. And was this a chiral center? Well, you know, I mean, I would say that it's a chiral center because you had a bromine, a hydrogen, CH3, CH2, so that's a chiral center. So let's say that this was a wedge, right? So now it's going to be a hash. So you should have a wedge hydrogen and then a hash methoxide. So that's an oxygen with a methyl group, okay? All right, but what if you're working with this one? Well, that's a potassium with an oxygen, and then it has a carbon, and that carbon has 3 methyl groups on it. So it sounds pretty bulky, okay? It sounds pretty bulky, so it's going to be a Hofmann favored. It's like this, and then Hofmann favored, this is Zaitsev, which is not good. You only use that for small bases, but we're working with this guy, so it's big and bulky. You're expecting him to go over here. You had a positive carbocation, so that's why I know to put it right there. And since it's Hofmann, I'm going to put on the least stable carbon, which is a terminal carbon, right? So it's going to be Hofmann. For this one, let's do an SN2 reaction. Hopefully you knew that it was SN2, because relative to this bromine, this halide, it's going to be a secondary carbon, and it's also a strong, right? So there's a metal that's a negative, so it's going to be strong, Sn2. Okay. Also, there was no heat given to us, so I'm just going to assume it's Sn2. Over here, we have chiral center, so whatever I'm reacting with, in this case my hydroxide, it should be a hash when I'm done with it. So we should have a wedge hydrogen and then a hash hydroxide, and our deuterium as well. Okay, so that's just a simple Sn2 reaction. But now we're working with triethylamine and heat, so it's going to be E2 reaction. In this case, it's going to be Hoffman favored. Okay, well, there's something that you should know. Okay, well, we're going to be taking out this bromine first, right? Pretty good, pretty cool, right? Okay, let's see. You should be expecting a double bond to the left. Why is that? Well, you're working with a big bulky base, triethylamine, and this may be on the exam, not this exact question, but the same concept. This methyl group is really big compared to this deuterium. Imagine deuterium as just a heavy hydrogen. It's still pretty small, but it's a bit heavy, okay? So a big bulky base is not able to go over in this side because it's too cluttered. There's too many big guys blocking you, okay? There's too many big guys blocking you. So I'd rather go to the left side where there are these small guys who can't block me. They can't block me, okay? So that's why I'm going to go to the left side, right? And you should be expecting something like this. So this is going to be Hoffman favored. We just have a hydrogen right here that's implied. Then we have some hydrogen right there. This stays the same. That's a pretty bad methyl group. Okay. And over here, what do we have? The deuterium pops off because if we had a double bond right there, the carbon would have 5 bonds, and that's not good. So we put it to the left side. We did that because CH3 is a bit bigger than deuterium, and it's going to be really cluttered for the triethylamine to actually come in and take the bond out, or to put a bond in, I should say. So because the left side is not as cluttered, we're going to favor the left side, right? Okay. So it's the same thing over here for some sodium hydroxide. I'm not going to do that. However, notice that you have something right here. You have a bromine, a hash hydrogen, and then a wedge hydrogen, right? Okay. Well, again, you're going to favor the left side. Why is that? Well, not only is the methyl group on the right side, you also have a cis hydrogen. So this bromine is a wedge. This hydrogen is a wedge. That's bad. For E2 reactions, cis is bad. Okay? So in no way are we going to be reacting in this side, okay? No way. So imagine that this methyl group didn't exist, and instead we had a hydrogen right there. So we had 2 hydrogens. Well, this wedge hydrogen is cis to this bromine. And so we're not going to go towards that path. We're not going to go on the right side. Instead, we're going to go on the left side. Not only is it less cluttered, but we have a trans hydrogen. And so that makes it better for when this hydrogen has to pop off. There's not a lot of strain that goes along, right? And so we're just going to draw like a simple one. Right there. And we just have a double bond right there, okay? Because that is like the cis-trans relationship, okay? So for E2, you can only do the double bond moving towards a trans hydrogen, not a cis hydrogen, okay? So trans is good, cis is bad. But what about number 5? Well, number 5, I have some reactant and I get some product. What do I need to put in to my reaction? Well, notice that this is a terminal alkene, and so terminal alkenes, they usually love Hoffman, right? And so I need something that would give me Hoffman. So I'm thinking, you know, maybe T-butyl potassium oxide with T-butyl hydroxide, also heat, right? So for sure that would be an E2 reaction, and the heat gives us a E2 reaction, and then these big bulky bases give us a Hofmann reaction as well. And so that would actually give you the terminal alkene. So now let's say that you have to do a acid reaction, right? An acid catalyst or something. Well, first of all, whenever you're working with acids, the trans rule for E2 is that it doesn't exist, right? So trans, or I should say cis, doesn't matter. Cis is okay. Okay? And that's going to apply for the last part for question 4. Right? So cis is okay. Whenever you're reacting with acids, you're going to be putting a double bond, and you're going to do like an acidic mechanism. So step 1, you should be utilizing your acid. What happens here? Well, let me draw out the sulfuric acid. So now our sulfuric acid is created, right? And what happens here is that this hydrogen goes away from this oxygen, and we have a partially positive hydrogen and a partially negative oxygen, okay? So what happens here is that this oxygen is very attracted to this hydrogen, and we create something like this. We create an oxygen that has 2 hydrogens sticking out, so we made a water molecule. We did this because hydroxide is a pretty bad leaving group, but water is a good leaving group. And now what happens is that this whole thing cleaves off. It cleaves off, and what it gives us is a positive carbocation, right? Okay, and we don't like that. And so we're going to do an E2 reaction. Actually, it's going to be like an E1 reaction, I should say, an E1 reaction, because you're not working with strong bases. There's no metal or everything. In fact, this is like water, and so that's going to be E1 reaction, right? And so what happens here? Well, we have some beta hydrogens. You have a hydrogen right there, some hydrogen right there as well. Which one am I going to prefer? Am I going to prefer this guy or this or that? Well, water is pretty small. And so whenever you're working with acids, they're going to give you a Zaitsev, right? So Zaitsev. So any acid reaction, right? If it's just like a simple sulfuric acid reaction, you're going to prefer Zaitsev. And that means that whenever I do my reaction, I should have something like this. And so my end product should be this right here. And let's do it like this, right? So that should just be the Zaitsev product, nothing special. The water eventually gives up its hydrogen. The hydrogen goes back to the sulfuric acid, and then we could just continue reacting as normal, okay? But what about this one? It's the same mechanism. The same mechanism. So this hydrogen goes to the oxygen, and this oxygen picks up this hydrogen. It then cleaves off, and it forms a carbocation, right? It's a secondary carbocation right there. Okay. Well, let's see. This is going to be a trans hydrogen, and this is going to be a cis hydrogen right there. Okay, but for acids, cis and trans, they don't matter, okay? They don't matter, right? So I could do this with a cis hydrogen, I could do it with a trans hydrogen, it doesn't matter for acids. But of course, we always want Zaitsev's rule, and so I'd rather have the bond going downwards, because if I did it this way, you have a 1, 2, that's disubstituted, versus 1, 2, 3, right? And so I'd rather have it going downward so I could get a tri-substitution. Same thing happens here. The bond breaks off. Hydrogen is loose. This oxygen picks up that hydrogen, makes a water, and then this water cleaves out, right? Water cleaves out. giving us this right here. Like a positive carbocation, this is a tertiary. Okay? So now what do we do? Well, you have 3 hydrogens right there, that's a beta. These are betas right there, that's a beta. But what am I going to prefer? Am I going to prefer doing this? Or this? Or am I going to prefer that? Or am I going to do this? Well, you're right. I'm going to prefer the center one. I'm going to do the Zaitsev rule. Because acids, they're very small. And so they're going to be, they're going to agree with Zaitsev, right? You shouldn't be expecting a Hofmann reaction. Right? Now over here, what do we do? Well, let's see. Let's say that this Z is a hydroxide group. Let's just say that it is. And that we do some sulfuric acid reaction, right? And heat. So of course it's going to be E1 reaction when we do it. But you're probably wondering, oh, well, whenever I do my reaction, I should be having a Hofmann reaction. No, you should be actually expecting the Zaitsev reaction. So it doesn't matter that one of the hydrogens is cis. It doesn't matter, okay? Cis is okay for acids. Now, the reason why we picked the right side is because we have a methyl group right there. And so what you would get is this, right? So we still have our deuterium and our hydroxide. The Z pops off and does its thing, you know. It was water, it comes out. So that was a positive carbocation. So we could go from the left or the right. I'd rather pick the right side. Why? Well, we have CH3 and a hydrogen, right? Like this. 2, 3. Actually, yeah, so what happens here is that this hydrogen forms that bond, makes a double bond, right? And so this actually shouldn't be hashes or wedges, it should just be a single line, right? It should be a single line. Oop. And since it's a single line, let's just do that. And we have a double bond. What do we have? We have 1, 2, 3. So that's a tri-substitution. It's really stable. It's going to be Zaitsev favored, and it's going to release the least amount of heat. So technically this is a beta hydrogen. I want to pull that beta hydrogen out the way to make that double bond. And the reason why I do that is because that double bond is going to be connected to a methyl group. It's going to be connected to this bond right there, and it's going to be connected to this bottom bond. And that makes it 3 tri-substituted molecule, which is super stable, super good, right? So now I wanted to talk about rearrangement. Okay, so what is rearrangement? Rearrangement is when you're doing a reaction and then you kind of like pause the reaction and move around some methyls or some hydrogens. So it's complicated when you try to explain it, but it's easier when you view it. So let's say that we're trying to do an acid reaction, right? So of course, this hydrogen, this bond breaks off to this oxygen. The hydrogen is loose. This oxygen picks up that hydrogen, and it forms a water, right? And then that water is a really good leaving group, so it's going to break off, and it's going to give us this, which is a carbocation. Notice that this is a secondary carbocation. What can I do? Well, notice that to the left of us, this beta hydrogen, or not hydrogen, but this beta carbon, let me kind of pull you aside for a bit. This only works if there's a beta carbon that is like quaternary, right? So this carbon has 1, 2, 3, 4 carbons attached to it. So it's going to be quaternary, okay? And it's also a beta carbon. So am I going to pick something to the right? Well, no. This beta carbon, which is quaternary, has a lot of sugar that I could borrow. And so this neighbor has a lot of methyl groups that I could borrow. And so what I can do here non-intuitively, it's not obvious, is that I could shift this methyl group to the bottom. Okay, I could shift it to the bottom where that carbocation is, and I get this. Okay, but now I basically transferred my carbocation charge, right? So this guy just moved here, this plus sign. But now look at this. Look at it. We have a 1, 2, 3. That's a tertiary carbocation. And you know, tertiary carbocations are more stable than secondary, and they're more stable than primary. So as you can see, this shifting of a methyl, which we call a methyl shift, also known as tunneling, is very favorable. It makes our molecule more stable. And so if you ever experience something, for instance, like you're doing this reaction on the free response portion of the exam, you want to pause the reaction and say, you know, can I do any shifting? Can I shift a hydrogen? Can I shift a methyl to make this molecule more stable? In this case, you could, because we were next to a quaternary carbon. All right, so now we have a tertiary carbon, or tertiary molecule. What can we do? We can do this. Let's see. Let's look at our beta hydrogens, or beta carbons. So we have some hydrogens right here. We have some hydrogens right there, yada yada, you get it. Pretty ugly. So yeah, what can we do here? And we have a hydrogen right there. Well, notice that we're going to favor Zaitsev because this is an acid reaction. And so we have to ask ourselves, which is more favored? Is this favored? Is this favored? Or is this favored? You know, the bottom, the purple one is pretty favored because we have more substitutions. Right? We have this. Notice that we have 1, 2, 3, and 4. Okay, 4. That's good. So that's 4. These are CH3s. We just formed an alkene, which is really stable. What if we didn't move the methyl? What if we just kept it like this? Well, then you would have something like this right here. Let's see, there's a 1 hydrogen right there. Yeah, there's no hydrogens over here, right? So the beta one is gone. There's no hydrogen. We can't use the hydrogen right here because you would still get another carbocation, which is not good. The only thing that we can do is use these hydrogens over here, which would just give us that, which is a terminal alkene, and that's pretty unstable. That would be Hoffman favored, and this is an acid reaction, so we're actually going to favor the Zaitsev, right, the Zaitsev product. And so, yeah, pretty much a methyl shift would have to be happening, right? It would have to occur. Now we're going to be talking about hydride shifts. Hydride shift is the same thing as a methyl shift, except you're not moving a methyl, you're moving a hydrogen. So when does that occur? When do we do that? Well, let's think about it critically, right? We're going to do the same type of acid reaction, therefore we're going to be favoring Zaitsev, right? And therefore trans or cis hydrogens don't matter. So one of the bonds break from the oxygen, it releases a hydrogen. This oxygen right here picks up that hydrogen and forms a water. It forms a water right there. Okay, and then water is a good leaving group, so it's going to come off, and we actually form a carbocation right here. And this is a secondary carbon cation. Can I do anything to make it a tertiary carbocation? Well, okay, well, let's see what happens if I move this methyl group, because, you know, we can only do it if it's beta, right? And so if I move this beta methyl over here, I actually get this. Do a hydrogen, let's do a methyl group right there. Well, what's the problem? Well, the problem is that you have 1, 2. And so that's a secondary carbocation. And you just basically repeated yourself. You wasted energy, you wasted calories writing this down. It's the same thing, right? It's the same thing. What can we do? Well, instead of doing that, what if we moved a hydrogen? What if we did this? What if we moved this hydrogen over here? Well, therefore you would get this guy, okay, and then a methyl group. But now you don't have a hydrogen right there, so we're going to say that's just a carbocation. But look at it. We have 1, 2, 3. That's a carbocation, 3 of them. It's a tertiary carbocation, right? And so that's really good. That's really stable. Therefore, we can continue the reaction. We can continue the reaction by doing this, right? We're going to have to put on our double bonds. And so what am I going to use? Well, you know, most likely I'm going to pull off one of these hydrogens over here. Let's do the wedge. And it's going to be Zaitsev favored, so we're going to do that, right? So actually like this. And let's do orange. There we go. So that's your product, right? You should have basically this product over here. And then we just use a hydride shift. Notice that the shifting a methyl would just do a repeat. You would still have a secondary carbocation. You know, maybe it's not obvious to do a hydride. Maybe you did a methyl shift first. If you get the same product, a secondary, and then you do another one, you get a secondary, try to do a hydride shift, right? Try to do a hydride shift. And if you get a tertiary or something more stable, stick with it. And then follow Zaitsev's rule or Hofmann's rule. In this case, we did Zaitsev. And you'll get your answer. So this is the preferred product. So now let's put this into practice, right? The R's just means that it's like some generic alkane branching off. So this could be like a benzene ring or something, or whatever. Right now we're just focusing on this substrate, okay? So it's kind of like a chain that's branching out. And for all intents and purposes, or whatever the American slang is that you use, let's just call this C. So you can think of the R's as just some carbons. We're going to do the same reaction. And so, hold on. So I've just taken the liberty to write out this sulfuric acid molecule because I think it may be confusing to you whenever I do, you know, this and then, you know. So it's kind of, I find like it saves time, but this is what I'm doing. The bond breaks, it releases the hydrogen. The oxygen picks up this hydrogen, it makes a water molecule, and then that water molecule leaves. And it gives us a carbocation. Okay, so that was all I was doing. Okay, so this is a plus sign right there. Yep. Okay, so now what do we do? Well, let's see what I can do. You're probably thinking, you know, I could probably move this R group. Let's say that's a methyl. I could probably move this R group, right? Well, what happens if I did that? What happens is we get C, 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 R, but now this one is a positive carbocation, right? So we went from a primary into a secondary. And that's okay, but can we do better? What if we instead did a hydride shift? What if we did that? So I'm like erasing all this, right? So let's do that. What if we actually moved a hydrogen, right? And it went over here. Well, what would we get? Well, we would get a carbon, another carbon, a carbon with a hydrogen. And that one still has an R group. You could treat it like another carbon. Okay. But look, Look at that. We formed a 1, 2, 3. I'm counting the R as another carbon because that's just like a generic carbon branch, okay? That's all I'm doing. Sorry, I didn't make that explicit, but the R in this example is just another carbon. So we instinctively made a tertiary carbon, okay? So that's gonna be a lot stable. And since we're doing an acid reaction, we're gonna favor the Zaitsev product, okay? So now I could take this hydrogen or that hydrogen or this guy, and I can make a double bond, right? So the real problem is which one do I use and where do I put it? Well, obviously I'm not going to make a double bond here because hydrogen cannot have 2 bonds, right? That doesn't make any sense. What if I put it over here? Well, we would have 1, 2, 3 things attached to us. Okay, what if I put it over here? We would have, let's see, 1, 2 things, 2 things attached to us. And you know what? I'm feeling like we should do this. So the reason why I picked the left one is because when we do the reaction, the final product should be 1, 2, 3. So technically there are 3 things attached to this double bond. If you can't see it, it's like this. Then we have, let's do R, and a carbon, and then a carbon, R, and a carbon. So it's a double bond. We have 1 group, 2 groups, 3 groups attached to that double bond. That makes it a tertiary alkene, and that's pretty good. It's really stable. It's Zaitsev favored. So yeah, that would be your reaction basically, okay? So it's not complicated. You just need to do a lot more examples. It'll be fine. Okay, so now we move on to the formation of alkynes. And how do we do dehydrogenation, I believe it's called, or dehydrohalogenation. There we go. Dehydrohalogenation of vicinal halides. So vicinal means within the vicinity, so it's very close. Notice that this bromine is within the vicinity of this other bromine, so we could say that these bromides or bromines are vicinal, okay? And dehydrohalogenation means that we're getting rid of hydrogens, we're getting rid of bromines or halides. So what happens? In this reaction, we're assuming that we have enough reactants to make a product, right? So what happens here is that this hydrogen is very acidic. Well, not very acidic, but it's acidic enough for it to pop off. And so what happens here is that this double bond goes to the carbon, and this NH picks up this hydrogen. And what we have now is R, C, H, with a bromine, a double bond to a carbon with an R and a bromine. So you're probably seeing a problem. You're saying, Brian, you can't do that. This carbon has 5 bonds. 1, 2, 3, 4, 5, right? And, I'd say, well, yeah, you're right. That's not possible. We can't do that. But carbon can actually shoot out a bromine. Why would it do that? Well, it's easier for bromine to pop off than hydrogen, right? Bromine is more willing to give up its bond. Hydrogen doesn't want to give up its bond too easily. And so this bromine, as a response to being overcrowded, it comes off. And so what we have now is this guy. And if you know the reaction, you know the answer, right? So now we have a positive carbocation, and this is a primary. Or not a primary, but it's a... Well, yeah, it is a primary. Sorry. Actually, secondary. Because we have a R group, right? So it's a secondary, and I don't like that. I'd rather be neutral, right? I don't want a positive sign. So instead, this hydrogen could go off again, and it could be picked up by this nitrogen. And now what we have is R with a carbon, and it's triply bonded. And actually, this arrow shouldn't be like that. It should actually be like this. Oop, hold on. Right? Okay. And now we have a triple bond with a carbon, a an R group, and a bromine. And notice that this carbon has too many bonds. It has 1, 2, 3, 4, 5 bonds. That's not good. I'd rather shoot off this bromine. And therefore we get a triple bond. Very fun. I thought it was pretty fun. And so all you have to do is just remember that this hydrogen comes off. It's picked up by this nitrogen, makes NH3. Right? NH3. And you basically rinse and repeat. You just repeat it so many times, right? And hopefully that makes sense to you. So that's dehydrohalogenation of vicinal halides. Very fun to say. Makes you feel a little smart. Okay, but now let's do another reaction. What if we had this guy? He's pretty important, and you should know him. What we're going to get when we do a reaction is, I believe it's called acetylide. And acetylide is pretty important, and you'll figure out why in a minute. Okay, so what happens here is that, again, whenever you have NH, and that should actually be NH2, not NH3. Oopsies. Oopsies, right? We all make mistakes, you know. Just a happy little mistake. That's alright. Alright, so now what happens is that, first of all, this hydrogen, it pops off. So it goes here, it's picked up by this nitrogen, and it actually gives us this guy, this happy little friend that we have. You know, you may lose some friends, but it's alright. You just have to learn to smile, right? Life brings pain, and you just have to go through it. Okay, so now we're a bit negative, but it's alright, it'll pass. And we have NH3. Okay, so that's called acetylide. If I spell it correctly, believe it's like this, acetylide, and it's with that. Okay, acetylide. Alright, so it's important to know that if it's this guy, this friend that we made, if we're reacting in step 2 with a primary carbon, then you're going to get an SN2 reaction. However, if you're reacting with something that is a secondary carbon or a tertiary carbon, you're going to get an E2 reaction. Okay, so now let's say that we're going to be reacting right here. Right, we're going to be reacting. So this is a primary carbon, obviously. And well, you'll say to yourself on the exam, well, this is a primary carbon and we're working with acetylide. Therefore, it's just going to be a simple substitution reaction. So now this chlorine breaks off and we form a positive carbon. And so these electrons actually are drawn to him and we get this. Right? And, you know, that was pretty simple. It was just a simple substitution reaction. But for this E2 reaction, we don't use acetylide. I mean, we do use it, but it's just to facilitate. So we're not connecting anything. If anything, we just take away this iodine bond. So he goes away. And he just forms a double bond, right? And so that would be your product. You don't use acetylide to connect anything. You just use it to rip off an iodine and move some beta hydrogens and make a double bond. So now let's talk about hydrogenation. Hydrogenation is basically we're inserting these hydrogens into the molecule. So we're saturating. Saturation just means that we're just stuffing hydrogens into the molecule, and we have to remove double bonds to do that. And so I need 3 hydrides, okay? Now if I only had 1 hydride, then my answer would look like this. If I had 2 hydrides, it would look like this. And if I had 3 hydrides, which in this case I do, it will look like this. Right? And so just for you to know, just all you have to know is, well, if you have enough hydrogens, you can remove all your double bonds and just make a simple alkane. And that's really good. That's super good. This is really unstable, okay? And this is pretty stable by itself. And so that's really good. Also, it has to be in palladium or whatever that is. Palladium? I don't know. Actually, in editing, this is actually palladium. So, all right. Anyways, continue the video. Let's roll. Okay, so it turns out that this reaction in palladium is called what? It's actually exothermic, right? So it's exothermic, and so you should have your chart like this, right? And so we started at 50 calories. Let's say we were gonna have 5 calories in the end. All right. So it's exothermic whenever you do hydrogenation. Okay. So now we're gonna be talking about nickel boride and Lindlar's catalyst. Okay. So nickel boride is just also known as a P2 catalyst. Both of them are actually going to give you a Syn addition. So a Syn addition just means that it's going to be cis. Okay, so it's just a fancy way to say that your product has to be cis. And so if you see on the exam that we're working with calcium carbonate, which is this Lindlar. Okay, so Lindlar. It's named after some chemist, Lindlar's catalyst, right? I don't like this S. Well, they're going to give cis reactions. So if you see this on the exam and you're seeing that you're working with Lindlar's catalyst and you get like a trans answer, that's going to be incorrect. Let's say that answer choice A, C, D, and E are all trans, but you know that Lindlar or nickel boride, they give you cis. Well, for sure, you're going to have a cis reaction and you're going to have a cis product, okay? So nickel boride and calcium carbonate in palladium is cis, okay? So it's cis. Okay, so here's an example, right? And what we see here is that we're going to do hydrogenation because we have an H2. We only have one H2, okay? So I know that my answer is going to get rid of this, and I'm going to have a double bond, right? But is this going to be trans or is it going to be cis? Well, I see that I'm working with nickel boride, and that means I have to be cis, okay? So here's what we do. I'm going to do this. Let's make sure that we're not adding any extra carbons. 1, 2, 3, 4, 5, and 6. Right? So I should have 6 carbons in the end. Let's do 1, 2, 3, 4, like that. So let's see. 1, 2, 3, 4, 5, and 6. And so yeah, for sure that would be the correct answer. I would say that is the correct answer, right? So this is cis right there. And let me see if I could draw that in a better way. Yeah, this one would be better. It really kind of like accents. It really portrays the cis relationship, okay? So that would be the correct answer. If I saw that on the exam, I would pick it, right? And yeah, it looks pretty good. This would be wrong. Okay, let's see. 1, 2, 3, 4, 3, 1, 2, 3, 4, 5, 6. That would be wrong. This is more of a trans relationship, okay? So that's bad. That would be incorrect. All right, and now we're working with Lindlar's catalyst. All right, so notice I only have one hydride right there, and so I'm just gonna get rid of one bond. So I should have a double bond in my final answer, and since it's Lindlar, it's gonna be cis. Right? So all we have to do is just do a pH, like that, and do a CH3, and a double bond. And of course, these hydrogens came in. So one hydrogen was there, and another hydrogen came from there. Okay? So these two hydrogens came there and there. And this is cis, so if you try to do a EZ configuration, let's bring this back so you don't forget. pH, which is a phenol or phenyl group, right? It's better than hydrogen, so that's going to be number 1. This is number 2. Going over here, carbon is better than hydrogen, so that's number 1. This is number 2. 1, 1, so we have 2, 2, 1, 1. They're on the same side, so it's going to be a cis, aka a Z. Right? So Lindlar and nickel boride, they are actually cis or syn. So this would be cis, Z, aka syn. So one thing that you should know is that for lithium, let's say that you're working with lithium. So we have sodium, Li, and NH2 in a liquid form, right? Not lig, but liquid. Well, this means that we're going to do something called an anti-syn. And that just means that this is going to be trans, or E, right? And I'm not going to do the reaction because it involves a radical from the lithium, and it gets really messy, okay? So, for instance, we can have R triple bond with another R, and let's say that we're running this through a lithium, and it's going to be NH3, or rather I suppose this would be NH3 as well, right? So that's not NH2 but rather NH3, my apologies, right? So let's say that we're running this into completion. I'm not going to draw out the mechanism, it's way too complicated, it's radical formation and all that jazz, not good. So this is actually going to be trans. So if I see this as an answer choice, most likely I'm going to pick it. If I see it's cis, I'm not going to pick it. So let's count how many carbons I have. I have 1, 2, 3, and 4. So I should have R, maybe like this. R directly attached to a carbon, like this, and then that. So I have 1, 2, 3, and 4. Okay, so that would be trans, and you're going to expect trans for a lithium, right? So this is kind of like a, this is an anti-addition. It's just anti means trans, so it's going to be E, right? And so that you should be expecting that for your product. No, you know what? No, I'm not going to do that. I'm not going to leave you hanging, right, per se. I'm actually going to do the reaction, because we're working with radicals, and I didn't want to talk about radicals, but I have like a guilty conscience if I don't tell you about it, so we're going to do it. All right, let's rewrite this. Right, so let's say that we have enough material to actually do this to completion. What happens here? What happens here is that a lithium comes in, and he actually donates an electron, okay? And let's actually erase this. So lithium comes in and he donates an electron. Let's say that this electron goes over here. So we have R, C, like this. But notice that this electron makes us negative. And let's see what is around carbon. So we have 1, 2, 3, 4 things around carbon. 5 actually. So let's see over here. It's going to be 1, 2, 3, 4, and yes, this one electron actually counts as 5. And you know what? I made a mistake. This actually should not be a double-headed arrow. Since we only moved one electron, it's just going to be a single barbed arrow, okay? So single barbed arrow means that we moved a radical. A radical is just one electron, right? So now carbon over here has too many things around it. It has too many things. And so it rather shoot off this bond, right? It rather shoot off that bond. So we have R, C, C, R, right? And we still have that electron. Okay, so where does that bond go? Well, the bond went over here. So these electrons came over here. We have 1, 2, 3, 4 things around us. That's 1, 2, 3, and 4. Okay, but since it's 4, that means that we brought a negative sign, right? We made this carbon more electronegative because it accepted some electrons is going to be more negative. Okay, so now here comes the fun part. The fun part is that we're going to be reacting with NH3. So since we're going to be reacting with NH3, let's draw it out. And let's do it in a different color. Right? Let's do it in a different color. Alright, well this hydrogen saw that this is a negative carbon, this is a negative carbon anion, right? And so it breaks off, and these lone pairs actually go and connect. And so we have R C with electron, carbon, and an R, and it goes over here. So as you can see, we're kind of making this out. We're kind of making it, right? Now what happens? What happens here is pretty simple. Another lithium comes in with a lone pair, or not a lone pair, but an electron, and he goes and he donates another one to this carbon. And so what happens here is that we have R, carbon with 2 electrons, C, H with an R. Okay. After that, we have 1, 2, 3, 4 things attached to that carbon. So that's pretty good, but we made this electronegative. And so here comes NH2, which is just an NH3, but we took away a hydrogen. And this hydrogen sees that there's a negative spot. And so he goes like this, and we connect them together. Right? And so now what we have here is going to be the R with a carbon. Let's do it over here. Like that. And so basically that's the same thing. We just have a trans relationship. Okay? And so what you just witnessed is that first this lithium comes in, it donates 1 electron to this carbon. The carbon takes it. He has too many things around him, so he shoots off a bond. That bond, the electrons that made the bond, they go to the other carbon. That carbon is negative, and this hydrogen sees that negative sign, and so this bond breaks from the nitrogen, and he forms another bond with this carbon. So that's what you see here. Another lithium atom comes in, he donates an electron, right? He donates an electron, and notice that your lithium should only have 1 electron because it's primary, not primary, but it's on the first column, right? So he donates 1 electron. We have carbon with 2 electrons, right? So 1, 2, 3, 4 things surround carbon, 4 things surround carbon, and that makes carbon negative. And so now the NH2 sees the negative sign, he breaks a bond from the hydrogen, and this 2 electrons merge with that hydrogen, right? And they combine. And so we're expecting a trans relationship, and we got it. And so now we're done with chapter 7. I hope that didn't take too long. I hope that it made sense to you and that you can at least do more practice problems, that you understand more, right? I hope that you understand this chapter more than you did yesterday and that you do well on your exam. And I'm just glad that you take time from your day to watch these videos. It really means a lot to me. And I wish you the best, and I hope that you do well on your next exam. Thank you. I love you, and be safe.